Okay, Omni-Directional Antennas by me, John, G8SEQ. This was a talk that, well, I revamped it actually for the QRP Club, hence the logo. Originally it was just a general talk on antennas. Go on to the next slide. So, what is an antenna? In radio terms, it's a device which radiates energy into space. And how does it do that? And it's by simultaneously generating and oscillating electric and magnetic fields which are orthogonal, i.e. at right angles to each other. So what do we mean by an omnidirectional antenna? It's one that radiates or receives from every direction in the horizontal plane. And probably the simplest type is a vertical antenna working against ground, something like this. So power comes up the feeder and the center conductor is normally the one that's connected to the vertical element, which is that black line, and the outer is connected to ground or earth. And in this instance, you're relying on the conductivity of the ground. The ground itself acts like a mirror. So if you were to stand a pencil on a mirror, you would see an image in the ground. So it behaves like a dipole. The ground does have another effect that it tends to push the radiation angle up in those directions. Being a bit slow. So for HF antennas, the vertical antenna gives a vertically polarized omnidirectional radiation pattern and is probably the only practical Omni HF antenna for the average amateur. Its radiation pattern is shaped like a donut, but as I've just explained, it's slightly distorted and it's pushed up into the at an angle into the sky. It's got an advantage over horizontal wire antennas that it requires only a small footprint if the ground is conductive, i.e. you don't need to use wire or mesh radials. So if you've got a good conductivity ground, then they can work quite well without radials. They do work very well on boats, particularly on seawater, which is more conductive than ordinary fresh water. Now, having said that, canal water tends to be quite conductive because there's all sorts of stuff goes into canals, and it tends not to get flushed out, whereas in a freshwater river, the most of the chemicals in the water tend to get flushed away. So you probably find actually that the surrounding ground is more conductive than a river. But anyway, we've had good results with using verticals on HF, either on the boat on the canal or actually connected to the sheet piling. Right, VHF antennas. You could use a vertical antenna as an omni, and a lot of people do, for 2 meters and 77 FM. Typical antenna would be a collinear or white stick, sometimes with elevated radials, and these are commercially available. However, most VHF DXs use SSB or CW, horizontally polarized antennas, usually a Yagi UDA beam. There is some scientific reasoning behind wanting to use horizontally polarized antennas for DX, and it's due to the fact that when electromagnetic waves like radio waves are reflected, particularly with mediums like water, the The vertically polarized wave tends to get refracted into the water, and the horizontally polarized waves tend to get reflected. And this happens at an angle known as the Brewster angle, which is 37.5 degrees. So there is some scientific basis for wanting to use horizontally polarized signals for DX work. Right, so why am I interested in Omni antennas? Well, the first horizontally polarized antenna I made was for 4 meters as a contest antenna. And the reason I wanted an Omni is because we didn't have a spare rotator, and this would have also complicated setting up. So it had to be some sort of Omni. And with everyone else in the contest being horizontally polarized, it's got to be horizontally polarized. Now, this choice also means that everyone in range, i.e. at less than the limit of propagation, would hear us all the time and keep clear of our frequency. That is only really effective if you're running a fair amount of welly, which we didn't have. But a lot of people didn't have a lot of power on 4 meters in those days, so we were pretty loud anyway. But it also meant that we would hear anyone who beamed in our direction, irrespective of where they were. So we just had to sit there and transmit and listen. So this particular antenna was a double turnstile, and as it happens, the gain on 4 meters was roughly equal to, or perhaps slightly better than, the average 4 meter beam of 4 or 5 elements that you could put up. A 4 meter beam with 4 elements on is over 10 foot long, and probably a 5 element would be nearer 12, 15 feet. So they're quite big antennas at the low VHF end, whereas the double turnstile just consists of dipoles, half-wave dipoles. So it's only 2 meters across, but they are stacked. The other thing about not having a rotator is the operators can't fiddle around with it to get already readable signals up in strength. Because it used to annoy me that when people, I'll just turn the beam round, and the VHF contests aren't really that hectic, although on bands like this you get ES openings which can last anything from 5 minutes to 5 hours. So if you get an ES opening, you don't know how long it's going to last. You don't want to be faffing around peaking signals up. And the other thing about this antenna is the local noise from the ground is reduced. You'll see why later on when I show you a radiation pattern. The disadvantage is they pick up QRN and QRM, noise and interference from every direction, which you can't null out. If you've got a beam, if someone's calling you a problem, you can often put them in a null and reduce the problem. You can't do that with an Omni, unfortunately. Oops. Right, this is a drawing I need to do that. Let's get back. This is a drawing that I've just picked up off the net of a typical collinear antenna, which is vertically polarized, and it consists of trap coils and things. You can make them all out of coax. I can't remember what band this one's for. Anyway, so that's a typical vertical antenna. And the reason I put that in is because I'm going to go on to the ESSEQue antenna. We're back really to HF now. This is a collinear fed dipole, and basically it's the top part of the collinear array that you saw in the previous slide. At the time I came up with this idea, I thought it it hadn't been used on HF, but later found out it dates back to 1948, the year before I was born, but in a slightly different form. And if I click on that link, it'll go to my website, hopefully. It might take a little while. Yeah. So if click on antennas and HF antennas, that's what it looks like these days. This is the antenna. Now this side can be just a piece of wire, but what I did in the early days was to reduce the ohmic losses. I actually connected the inner to the outer at this point, which is this is actually the feed point of the antenna. The power goes in here and it looks like an end fed, but it isn't really. And what happens is it goes round this coil and then up there, and then when it gets to here, it can't go anywhere, so it transfers this to the outer. What's coming up the inside of the coax, the inside of the outer, that is, has to flow back down here to this coil. But this time, this coil's acting as a trap. When the RF goes up in the first place, it doesn't know it's in the coil, it just thinks it's going up coax. But when it gets to here, the capacitance between the turns and the inductance of the turns forms a tuned trap. Anyway, if you want to read about that in detail, you can do. And this is the original form I had on it with transformers and all sorts in, which I found weren't actually necessary, so I did away with them. Right, omnidirectional beam. This sounds like a bit of a contradiction. So how can it be a beam if it's omnidirectional? Well, all the previous antennas except the VHF collinears have little or no gain over a dipole. But the following antennas or turnstiles have gain because they have a narrow vertical beam width. But unlike the collinears, they're horizontally polarized. And here's a photograph of my 4-meter beam, double turnstile. So we've got a half-wave dipole across there and another half-wave dipole across there, and it's duplicated down here. Now, in order for these to work, all of these elements have to be fed in phase. So this element here would be connected to the inner of the coax, and so would that one, and this one to the outer, and then this one and this one connected to an inner, and these connected to the outer. But the power's got to be split between the two sets of cross dipoles, and the phase has to be preserved. So you've got to cut your feeder to the right length, taking into account the velocity factor of the cables. All of that is explained on the website. Right, it's got a substantial amount of gain, about 8 dBi. Dave ORG has measured his, and he reckons he gets about 9 dBi. It depends somewhat on the height that you mount it at. And it's in all directions in horizontal plane, ideal for DX working. The radiation pattern's not quite as flat as a pancake, but slightly dished like a dinner plate, and this has some advantages. The main lobe is pointing slightly above the horizon, which helps with tropospheric propagation, and it also cuts down received noise from the ground, as I mentioned before. Helping with tropospheric propagation, what it is you're pointing at a you pointed at a piece of sky which is just above the horizon, which allows some refraction to carry the wave over the horizon, and it all works by phasing. And this is a typical phased array. It's not an omnidirectional antenna, but in this one, these gamma matches crossing over like that, they control the phasing, and also the lengths of the different lengths of the directions and reflector control the phasing. So this one produces a beam which goes in that direction. With a double turnstile, the phasing is such that the beam goes out in all directions, but it's the phasing causes it to be squashed down into this dish shape that I was talking about. I'll just explain that. Right, some antenna myths. I left this in from the general thing. It says there's no such thing as a non-resonant antenna. People who claim to have one are just using an antenna that isn't resonant on the frequency they've chosen to operate on. And the other myth, twin feeder is inherently less lossy than coaxial cable. It's just not true. It depends on the dimensions and the construction. And I could give you an example of somebody made some twin feeder up out of what he thought was copper wire, and it turned out to be extremely lossy. What he didn't realise that the wire he bought was very thin, because he wanted to hide it basically, but it was in fact beryllium copper, and it worked more like resistance wire than the transmission line, so it worked as a very good dummy load. Right, some practical antennas. For a simple antenna, you can't beat a dipole, but you can improve its mechanical and electrical design from standard pattern. So the collinear fed dipole, aka resonant feed dipole, which I think is a misnomer, and mistakenly believed to end fed. Right, so why is it better than the standard pattern? It uses less materials and therefore lighter and less losses, as this represents the shortest possible feeder, especially when used as a sloper or vertical, either from a high building or suspended from a balloon. And yes, I've tried them all. I made one for 80 meters, and I flew it from a kite, actually. That was from the local park in Caledon Park. Remember, we had a talk some years ago by somebody who was into kite antennas, and he gave the talk on the Friday evening, and on the Saturday we went over to the park and tried it out. And this collinear fed dipole acted as pretty much a vertical antenna, because what we did was we suspended it from the kite string just below the kite. So that worked really well. When we could get it to stay up, it was a bit gusty that day, and the controlling the kite was was a bit tricky, to say the least. These collinear fed dipoles, they can be adjusted to compensate for the presence of ground, because its feed point can be offset slightly by coiling or uncoiling the trap. You can go to my website for the current design. Right, I should mention travelling wave antennas. These can be used in the vertical plane. These have a load at the far end, and the load absorbs any power that was not radiated by the wire. The advantage of these is they, because they've got a load on the end, the SWR is always close to 1-to-1, but they're not very efficient. They're easy to make. You can just put a dummy load on the end of a piece of coax and reverse the connections to the feed point, so the RF flows down the outside of the coax. I got that idea off a German who forgot to pack his antenna, but he did have a length of coax, 50 ohm feeder and a dummy load, and he managed to work quite a few people with it. I've already explained about the mirror effect of the ground. It tilts it upwards. You can vary the tilt for a vertical antenna by using a skeleton ground plane made of radials sloping downwards. So elevated radials will improve the antenna performance, particularly if you're in a place where the ground conductivity is not very good, but it will also alter the angle of radiation. So this would be a vertical with sloping radial. This is a diagram that I just borrowed somewhere on the internet, and often these radials slope more like 45 degrees, but you can set them at any angle to suit your purpose. Right, back to the turnstile antennas. Basically, they're pairs of horizontally polarized dipoles, but you need this 90 degree or quarter wave phasing line to get the phasing correct between each pair of quarter wave elements. Basically, this produces a circularly polarized signal which goes straight up in the air, but as you come down at different angles, it becomes elliptically polarized and then practically horizontally polarized at the horizontal plane. The double turnstile is two of those elements stacked with the phasing harnesses, and you also get an image in the ground like you do with the vertical antenna. This increases the gain and alters the radiation pattern such that it's aimed at a point just above the horizon. And that's what the pattern looks like. It depends on the height that you put it above ground in terms of wavelengths as to what the pattern. This lobe is almost all horizontally polarized. There is a little bit of vertical in there. That's the vertical polarization, and this is the horizontal, and the outer bit is the combined radiation pattern. And I don't know whether you can read the figures, but it's 8.652 dBi according to this computer program, and the takeoff angle is 11 degrees. Beam width is 10 degrees. Side loads are a bit of a nonsense. If you were to look down on this antenna to see its omnidirectional pattern, you find that it's not quite a perfect circle, but there's only about half a dB difference between, well, there's 4 points. There's one there, and one there, and one there, where it's half a dB lower. It's almost a perfect circle, but not quite. And you wouldn't notice by listening to signals coming from different directions that there was any difference. So it's a pretty good Omni. Trying to work. Oh, this is the one I made for 28 megahertz. Very effective antenna on 10 meters. It's got a lot more gain than something like a tri-band beam that your average amateur might put up for 28. This has got 8.5 dB gain. So it's quite a potent antenna on HF. It's the lowest frequency I've made one for. You go up in frequency and get the antenna higher, this lobe comes down to about 6 degrees. Right, this shows the typical turnstile radiation pattern for a single. That's just a pair of cross dipoles, or as you'll see later on, they don't have to be dipoles, they can be loops. Here's one that uses loops. This was, I've forgotten his call sign, he's the SK now, he's Chebik. Bob's built one of these for 6 meters. The only awkward thing about it, it needs, I think it's a 100 ohm phasing harness. We didn't have any 100 ohm coax to make one, so we made it up out of twin feeder. But this is just basically wooden sticks or bamboo canes supporting a wire square loop. But there is another one which is not so obvious. It's this wire here, and that is another one of these sticks pointing at you. So there's one coming out of the screen and one going back. So it looks like an octahedron, which is an 8-sided figure, bit like a cube. Anyway, that's only got about 6 dB of gain. Yeah, go back to here. Outer ring 5.7, so it's just slightly less than 6 dB a gain, whereas the double turnstile had got about 8.5. So a bit less gain, but still quite an effective antenna, as Bob will tell you at the end of the presentation what he's worked on his antennas. And here's another one. Now this antenna I really like. I've actually built one of these myself. I didn't make a very good job of building it because it mechanically it wasn't so good, and it did fall apart. I've still got the bits. I'm planning to remake it, but I've built it to K4ERO's instructions. Excuse me, I need a drink. I built it to the instructions, and the SWR came out at 1:1. The reason for this is these loops are rectangular with a 2:1 aspect ratio. That is, this side here is twice as long as that side there. If you do that and feed it, well, you probably wouldn't want to feed it at the top. So if you feed it down here in the middle of the short side, it has an impedance of 100 ohms, but then you've got another loop here which also has an impedance of 100 ohms. So you just connect them both together at this point, so they're connected in parallel, and you just feed it directly with 50 ohm coax, because you've got 200 ohm loops in parallel giving you 50 ohms. The only other thing that you need to know about this is the phasing isn't done the way I did it with the double turnstile. The phasing is brought about by having these two rectangular loops, slightly different sizes. So one is undersized for the frequency and one is oversized. So one's slightly low in frequency and one's slightly high in frequency. And if you look carefully at the construction, this wooden boom here is below that one, but at the top, the equivalent to that one is above and that one. So this one is the longer loop and that one is the shorter loop. Right, there's a bit distortion in that drawing, but anyway. So that causes the 90 degrees phase shift that you need to generate the omnidirectional pattern. And it's very quick and easy, cheap to make. And we made them out of wooden wire, and you'd probably spend no more than £5 on materials if you bought everything new, and most of that would be the connector for the coax. So the loops are both close to a wavelength long, and I think that design's absolutely brilliant. Oops. All right, on the advantages and disadvantages. Advantage: no rotator required, cuts costs. When I said that antenna, including the feeder, you could do for about £5. Currently, rotators, I've said they're 5 times the cost of the antenna, but this was based on a commercially made beam antenna made of aluminium tube. So you're probably talking about anything from 50 to 100 quid for the antenna. So you could be talking about 500 quid just for the rotator. So I was quite shocked by the when I looked up the price of some rotators recently. That's the sort of money they're asking for them, albeit they're capable of rotating quite a heavy beam. But if you've got a stack of antennas, you know, there's several different bands, it's going to be the same weight or more than an HF beam. Previously, the rotators I've used, apart from one that was given to me, which was a TV antenna rotator, and it wasn't very good, it packed up eventually. I've built my own rotators at very little cost actually, but they weren't brilliant, but they did work. And of course, then there's the Armstrong method, which I've used. I did have an antenna that went through the apex of the roof with a Tommy bar on it. I could twiddle that round. That was the best rotator I ever had actually, because I could turn that as fast as I like. So for the VHF bands like 6 meters and 4 meters, the double turnstile has more gain than the 3 or 4 element beam that most amateurs could put up. I know some of the big stations do stack a couple of beams one above the other on for 4 meters and probably 6 meters as well. Some people have got acres of land and have huge towers, but they're spending thousands, whereas the double turnstiles that I make, if you'd be hard pushed to spend more than 20 quid on them, buying all new materials, aluminium tube, and say these wooden wire ones like the ERO design you could make very cheaply. If you go up in frequency into the high VHF bands like 2 meters and 77s, they've got less gain than the average beam that amateurs use. So 2 meters is about as high as I want to go with a double turnstile. They are very effective, as Dave will probably tell you. He's had a recent fairly DX contact, considering the band conditions were relatively flat. But I have made a quad turnstile, not to be confused with the turnstile quad, which is the other name for that octahedral antenna I showed you. But that's only got 11 dBi of gain on 77s, so it's not a brilliant antenna, but it does work. And but you know, 77's beam's fairly light. You could have one with you know, 14, 15 dB again easily, and it wouldn't be very big. Some people are obviously using a lot longer antennas than that. And as I said before, they pick up the disadvantages. They pick up noise from every direction. That's about the only disadvantage that I can see. I sort of just mentioned. Yeah, got ahead of myself. Right, here's an interesting antenna, the Omniflyswatter antenna. I only ever used this once in anger, just to prove that it worked. The way I implemented it on that occasion was a bit cumbersome. I keep threatening to rebuild it in a more portable form. But basically, you use a circularly polarised feed to a dish antenna. You point the dish up in the air, and you have a reflecting cone, which replaces the traditional flyswatter antenna uses this arrangement, but not necessarily circularly polarised, and it uses a flat plate which is trapezoidal. But what I've done is I've bent that flat plate round into a circle or a cone, and it has to have an included angle of 90 degrees, so that this is at 45 degrees to the horizontal, or 45 degrees to the vertical. And basically you pump RF up to the cone, and it goes out in every direction, this way, this way, this way. And people think that it doesn't work. I know it works because I've tried it, but they're saying you can't have the sort of gain that I claim because it's spreading the signal around in 360 degrees. But I maintain that it's actually being electronically rotated at the speed of whatever frequency you're transmitting at. So you still get the full gain from the dish, less some losses due to under or over illumination of the cone. So the cone needs to be sort of slightly larger than the dish, really, to get the maximum benefit. But you don't want to make it so big that it becomes really cumbersome. So that's the Omniflyswatter. I keep threatening to make one for 10 gigahertz as a demo antenna, which would be easily portable, but at the moment I haven't got a circularly polarised transmitter. And lastly, before I go on to the last slide, the Omniflyswatter will work on any SHF or microwave frequency, although I've only ever used it on 23.7. And the vertical beam remains the same as the dish would have had if aimed horizontally, typically about 3 degrees beam width. But I claim that it's rotating because of it, because of the way circular polarization works, and but it's so fast that it seems to be radiating in all directions at once, but it isn't really. And lastly, I should mention the Omni-Vee antenna. They seem to be favourites of broadcast TV transmitters, which is where Paul G4IEV got the idea from. I've never built one, but I've used one. I've used Paul's in contests. He built his on a triangular lattice tower, and I can't remember now whether it was 3 or 4 sections, but it was a bit of a pig to put up because it was quite heavy, and he had a van with a roof rack on that he used to have to use to transport them. So they weren't very portable, although we did use them in VHF NFD, which is, and I saw how effective they were because of their omnidirectional properties. And the phasing harness consisted of a lot of coaxial wire, coaxial feeder, and it was a funny impedance. I can't remember what the impedances were that he used, but I remember the outer of this coaxial cable he got was quite interesting because it was pink. I've never seen pink coax before. So that's it, folks, as they say. I'm open to questions. Click to exit presentation. I can close that down there, I think.
One quick question, John.
Yeah.
The double turnstile antenna, would that work on the third harmonic as well? I don't see any reason why not, because it's just the standard. They're half-wave dipoles.
It does work on the third harmonic. They all do, but the impedance won't be 50 ohms. Well, it's not 50 ohms anyway. The best SWR I could get was less than 1.5 to 1. I've never tried getting it down. I know Chris Sidney played around with the element lengths to try and get the SWR down. But what happens though is when you go up in frequency, it's no longer omnidirectional. It turns into a cloverleaf pattern.
Right.
I did do some modelling on LNEC with it, but I did actually use the quad 77s turnstile on 23/7s just for the hell of it, and we did workstations, so you can use them on the third harmonic, but it's not Omni anymore.
Yeah, makes sense, because obviously the phasing harnesses will be the wrong lengths.
Well, the phasing harness will still work because it's 3/4 of a wavelength instead of a quarter, but it's the way the elements radiate, because the radiation pattern from the elements is not the same, is it?
Yeah. Cheers.
It's quite effective though, because you could put one of those up with a cloverleaf pattern and just sort of rotate it through 45 degrees and to fill in the gaps. You put two up side by side and have them at 45 degrees to each other.
Yeah.
And use the power. Actually, I wonder what would happen if I'd have to try and model it, if you twisted the top pair 45 degrees in relation to the bottom pair to use on the third harmonic. That might work.
Yeah.
But then that would affect the radiation pattern on the primary frequency though.
Mind you, to be fair, the size of a 77s one's going to be tiny anyway, so you might as well build one for 2 meters and 77s. That's what I was thinking.
Yeah, well, the 77s one I built is the quad turnstile.
Well, yeah, because again, that would still be quite small.
Well, it is. It's well, the elements are only this sort of size.
Yeah.
Across, and there's 8 of them.
Yeah, very interesting. Cheers, John.
Any more questions?
I've got a couple of questions, John. How critical is the distance between the top turnstile and the one below it?
Yeah, it's critical. They're a wavelength apart. The dimensions are given on the website, but yeah, if you've got the wrong spacing, the phasing will be wrong.
Okay.
Was it? No, it's not a wave. It's a wavelength or a half wave. I can't remember now. Look on the website.
Okay. And then when you look at it like from the top, a bird's eye view, are those top and bottom turnstiles in line with each other, or are they kind of, is the bottom one 45 degrees off from the top one, so you've got more of a star type?
It's got to be completely symmetrical. So
symmetrical.
The top looks just the same as the bottom.
Yeah. Okay.
Otherwise you've rotated the phasing. You no longer got the 90 degrees phase shift, or the top and bottom elements are not in phase with each other. That's what happens.
And the distance from the ground, is that still the sort of distances you'd have for a sort of a normal dipole, a standard dipole?
Well, not really. For VHF, you tend to try and put your antennas as high as possible to get them to work as free space antennas. But these antennas work best when they're specific heights above ground. And what seems to work best is about 1.5 wavelengths. So
Okay.
We were restricted in our contest station by the rules. So our antennas are on the top of 20-foot scaffold pole, which is, well, roughly. So the bottom elements were just above a wavelength on 6 meters.
Mm-hmm.
We ended up using them as well as 4 meters. We used them on 6 meters, 2 meters, and 77s eventually. Made antennas for all those bands. But as I said, the first one was built because we hadn't got an antenna for 4 meters. That's what I came up with. Dave helped us build it. It took about an afternoon to make, didn't it, Dave?
That one, the K4ERO wheel that I made, I made 2 of them, but mine's only about 8 feet off the ground. And I've worked into the Balearic Islands on 4 meters a couple of times.
Wow.
I've worked 17 DXCC countries with it. Right, I'm running about 50 watts, but that's what I've managed to do over about 3 years. As I say, mine looked quite crude, but I've got fair long run of coax on it because of where I've stuck it. But if you probably was slightly engineered slightly better, you probably wouldn't need much coax on it. And that's the other, what was it? There was a contest on last Sunday and I worked a portable station that was what, about 150 miles away.
Wow.
And
I guess they're, I may have missed it, but they're full wavelength loops then to be 100 ohm impedance. Is that right? And you've got 2 of them in parallel to give you your 50 ohm.
Yeah, as John said, one is at a lower frequency and one at a higher frequency of your center frequency.
Yes. Okay.
It's only about 5 or 10% difference, isn't it?
Yeah, something like that.
Interesting.
And as I say, I've had one of
ratio of the sides that gives you the 100 ohms.
Yeah.
Oh, okay.
Mine flops about a bit in the wind, but it's still there, but I've just screwed it on the side of a shed, just on a sort of wooden type mast. But it probably, if it was slightly better engineered, perhaps I used some slightly thicker wood. So it's very thin what I've used.
Yeah, mine fell apart because I just used wood screws to screw it together, and what I should have done was use bolts with washers on.
But that's my record with it. I mean, I'm trying to think some of the countries. I've worked into Finland, into Norway, Poland many times, Hungary,
Slovenia, Croatia.
Spain, yeah, Slovenia, Croatia, Spain, the Balearics. Worked Germany. They've only got limited facilities. Trying to think where else. It's one or two of the countries you might expect to have it don't, like Sweden. So that's what I've managed to do with it over a period of 3 years. And it's to say, for a fiver, you've got an aerial that's equivalent to what, 70, 80 pound 3-element Yagi.
Yeah, impressive.
And I've got all of those countries I've got confirmed as well. So it's not me just saying it. I've actually got confirmation of all of those countries. Mostly I use Logbook of the World, but I had 1 or 2 QSL cards back. Oh, I've worked Holland as well. That's another, that's not so far though, is it?
What did you use on your you mentioned, I think a couple of weeks ago, John, that you'd made a contact from, I think it was, did you say Sydney to Ireland or Australia to Ireland? Was that on one of the antennas that you showed tonight?
Yeah, that was a collinear fed HF dipole for 20 meters. It was on the 20-meter band. I put that up as a sloper though, rather than an omni, because I threw it up a convenient gum tree. And I also used my friend's swimming pool, which was about a quarter wave on 20 meters, as a reflector. So it's got salt water in it.
I mean,
Very nice.
we took the two of these aerials, didn't we, to Fair Isle? We had one on 20 and one on 18 megs. And 20, I think I worked into the Falkland Islands. And on 18, we were working all over the place. And to the west coast of the States, we had almost a daily contact with a guy near Seattle. We were getting some really hefty reports. Okay, we'd got the Atlantic Ocean as the ground plane, which made a big difference, but very simple.
That was funny when that USA station actually what the ground plane was. He said the Atlantic Ocean.
The ocean.
Yeah, we were about 30 yards from the ocean, and then
we were operating from a lighthouse on Fair Isle.
So that was one that John made for 20 and one I made for 18 megs.
And that's just a quarter wave section, I think you said. Is that right?
It's 2 quarter wave sections. It's a half wave dipole.
I've got you, yeah.
It's actually fed in the centre, although it looks like an end fed because you're using the feeder as the radiating element.
I'll have to have a look on your website again, John, to remind myself. But
I've had several of my students make them, and I loaned my original 40-meter one to one of them. And when I asked for it back, he says, "No, you can't have it back. It works too well." I'm not joking, and I never did get it back. So I said, "Don't worry about it. It didn't cost much to make." So those, I mean, I was given a load of coax, and I made them out of that. It was Ethernet cable, actually, the first one to make. So they cost me next to nothing to make. So the most expensive part is the PL259 on the end of the coax.
the plug, yeah.
So is that a bit like the collinear? A bit like, is it a T2LT type antenna, which is like an end-fed dipole where you stick you basically strip your coax back at a quarter. You take the braid off at a quarter wave, and then you put a choke at a quarter wave down the coax again. So the you're basically using.
Yeah, it's the same idea, but I coiled the feeder up to make it when I first thought about it, I thought I was just making a choke. But in fact, it turns out it's a tuned trap. So it's actually quite critical to adjust to get it to you get that to resonate at the frequency.
Yeah, because
the way I've constructed it, you can add, say, a quarter of a turn one end and drop it off at the other. If you do that, you're effectively moving the feed point. You're making it slightly offset from the centre of the dipole. But if you add a quarter of a turn on, or even a half turn, you're changing the resonant frequency of the trap then.
Yeah, because I've got a 5/8 wave T2LT type antenna that I use for 11 meters.
I did it all experimentally when I first made them. I didn't bother calculating anything, and I got lucky, I suppose, because I guessed at the number of turns on the coil, and it turned out to be almost spot on. And when I'm out in the field, I can adjust all these antennas in about 5 minutes. Don't need an ATU. Get the SWR down to 1-to-1 on one band. They also, strangely, and I'm not quite worked out why, they also work on the subharmonic. So a 20-meter one will work quite well on 40 meters, although its efficiency is a bit lower because it's only a half-size aerial one.
Yeah, well, that's interesting.
Mm.
So I must
Useful.
have a go. I've got an 80-meter one that I use as a permanent installation at home. I must try it out on top band. I very rarely go on top band, so I'll give that a go one day next week, I think.
Found the one for 18 megs. Here it is. This is the coil. And it's all coax, as you can see. So and this is the very one we were working that guy in Seattle most days. Mind you, when we looked at his, he got an aerial farm. He got a 4-element beam on 18 megs, but it's just made of coax. Nothing else, nothing less. And this is the very aerial that we stood all the battering at the South Lighthouse on Fair Isle.
I worked out it's the shortest possible feeder you can have to an antenna. I used the 20-meter one in the Isle of Man once. I used a fishing rod on the top of a sand dune for the far end of the antenna, and I hid from the wind in the dip. And the feeder to the coil was less than 2 meters. The coil itself, though, is about a quarter wave, and then you've got a quarter wave to the feed point. So the total feeder length is just over half a wavelength. That's what you can get away with when you're out portable like that. At home, the one I've got's got a much longer length up to the coil, because I actually use the ceramic chimney pot on one of the unused fireplaces as the coil former. Got 10 turns. That works really well, that one. It's the SWR is pretty good down at 3.5 megs, but it's not so good up the high end of the band, the phone end. So I use it for every band with an ATU, but so you can if you cut one for a particular band, you don't need an ATU, and you can just play around with the coil to get the SWR down to something sensible to stop your rig shutting down, which is important if you're using something like an 817. You've only got 5 watts. The SWR is too high, the power folds back, and you're only putting it out, a watt or so.
Yeah.
I mean, that's quite a good band to get on if you're fairly new to the hobby, because it isn't so competitive as 20. And it's, well, it was August, wasn't it, John? We went.
Yeah.
August 2012, was it? Not the best time to be working across the pond, but we were getting a long way. I can't remember the furthest contact we worked. I don't think we worked into Australia, mainly because I don't think we could get up that early. But we certainly worked across the USA, into Canada, might have worked the odd South American, loads around Europe. So
Impressive.
very simple. And on John's website, just follow the instructions.
Yeah,
again, this is just
a lot easier than some. There's some very similar designs out there, but I thought they were a bit fiddly.
I've got one of those. I'll go and see if I can find another design of them, but that's just made out of whatever it is, 50 ohm. What is it, RG? Is it 59? 58, 59, the 50 ohm cheap and cheerful coax. I'll go and see if I can find that other design. Talk amongst yourselves. I'll be back in about 5 minutes.
I made a portable one for 80 meters made out of RG174, which is very thin coax. So it's relatively light in weight. It probably only weighs about a kilogram. I mean, it's quite a lot of wire, 80 meters. And I've used them as NVIS antennas, just drape them along a hedgerow, only 8 to 10 feet off the ground, and worked all over Britain with them. And
is it
6 meters, not 6 meters, 60 meters, 5 megs.
Is it a sort of a quiet antenna, John? Is it because I guess it's balanced.
Yeah, I wouldn't say it's particularly quiet. But I use them a lot in out portable in relatively quiet locations. I've got a problem. I'm pretty certain it's VDSL because I get an S9 noise level on 80 meters